All right. Hi, everyone. Thank you for coming. I am Andrew Chen, and that is Dominic Torno. And just to give you some context, like this kind of came out of a project from SIGDocs, where we're using systems modeling to try to explain how Kubernetes works better. So this is sort of like a case study with the scheduler. And then let me give it to Dominic.
Thank you. Hold on, I almost got it. Yes. All right, just a quick question because I'm curious. So for myself, I had the hardest time when I got started with Kubernetes to wrap my head around it. I have the hardest time to understand what it actually is, and I had the hardest time to understand how it works. Does anybody else share this feeling or? All right, cool, yeah, a few of us. So I would argue that Kubernetes does have a problem with complexity. However, I would actually argue that Kubernetes has a problem with its perceived complexity. The perceived complexity of Kubernetes is very high. However, the conceptual complexity of Kubernetes is actually fairly low. It has a few basic patterns that it applies over and over. And the understanding of Kubernetes relies on the understanding of these patterns. So I believe that the problem is a problem with communication and not a problem with engineering. So as Andrew already said, this presentation is part of a larger collaborative effort between the CNCF, Google, and SAP to advance the standing of Kubernetes and its underlying concepts using a systems modeling approach. So at the end of this presentation, please do share your feedback about the modeling approach that we use in this presentation. So we talk about modeling, so let's model the scheduler. This diagram depicts a high-level architecture of Kubernetes. Like every other component of Kubernetes, the scheduler monitors and modifies objects in the Kubernetes object store. The sequence of events and actions around the scheduler can be summarized as, after a user or controller creates a pod, the scheduler, monitoring the object store for unassigned pods, will assign this pod to a node. Subsequently, the kubelet monitoring the object store for assigned pods will execute this pod. So in summary, we may informally describe the task of the scheduler as the scheduler assigns a pod P to some node N. But that begs the question, what is an assignment of a pod to a node? So diving deeper, this diagram depicts the Kubernetes objects that are involved and of interest to the Kubernetes scheduler. Kubernetes represents a pod as a Kubernetes pod object, a node as a Kubernetes node object, and the assignment of a pod to a node as a Kubernetes binding object. Please note in this diagram, there is a node name in the pod spec that we will come to later that assigns or actually pre-assigns a node to a pod before it is actually being scheduled. And please also note the scheduler name in the pod spec to assign a custom scheduler to a pod. We will entirely ignore custom schedulers in this presentation. So equipped with this knowledge of Kubernetes objects, we can now define that a pod P is assigned or bound to a node N via a binding B if and only if the binding's name equals the pod's name, the binding's namespace equals the pod's namespace, and the binding's target name equals the node's name. The existence of this binding signals to the kubelet on this node to execute this pod. So equipped with this knowledge, we may now formally describe the task of the scheduler as the scheduler for a pod P selects a node N and creates a binding B so that the binding's name equals the port's name, the binding's namespace equals the port's namespace, and the binding's target name equals the node's name. So conceptually, the Kubernetes scheduler loops over unbound ports, and in the case of pre-assignments, creates a binding to the pre-assigned node, or in the other case, selects a node, if it can find one, and binds the port to that node. So this is a specification of the control loop of the scheduler in TLA+, temporal logic of actions. The control loop of the scheduler is actually fairly straightforward. Now, let me add this, all right? The scheduler is a complex piece of software. It has many, many lines of code. It is not easy to understand. However, the specification of the scheduler is actually fairly straightforward, fairly simple. It is one loop, it has one if statement, and it selects a node for a pod. So the complexity of the scheduler is apparently in the selection process of the node for a pod. So let's dive into that. Selecting a node is a two-step process. First, the scheduler selects a subset of nodes that are qualified to host this pod. And then second, the scheduler selects a node from this subset with the highest rating for this pod. So we had two kinds of functions. We had filter functions for qualified nodes, and we have rating functions to score nodes. Let's look into some of the filter functions. So the filter function is basically a conjunction. The overall filter function is a conjunction of many individual functions that are predefined or predefined in the scheduler. So let's start with a simple one. Let's start with a few sanity checks. So this diagram depicts the relevant attributes of a node for the sanity checks. Most importantly, we have unschedulable, we have running, and we have ready. So the filter function here, the scheduler may assign a pod P to a node N if and only if the node spec unschedulable equals false, the node status phase attribute equals running, and the node status condition collection contains a node condition so that the condition type equals ready and the condition status equals true. Any node that does not pass this filter will not be considered for scheduling. Let's look at another filter function, famous taints and tolerations. So this diagram depicts the relevant attributes for taints and tolerations and takes the pod and the node into account. Quick highlight, the tolerations are defined on the pod and the taints are defined on the node. And just like before, we can define it with actually a simple expression of what taints and tolerations do. And the scheduler may assign a pod P to a node N if and only if for each taint that is an element of the node's specs taint, there must be a toleration that is an element of the pod spec toleration so that the toleration matches the taint. Once again, if this is not the case, the node is not considered qualified for hosting this pod. Similar, always the same pattern, it comes to affinity. Personally, I have to say I had a harder time wrapping my head around taints and tolerations and an easier time, right, to understand affinity. I was actually surprised to see that the data structures for taints were actually very little and innocent, and the data structure surrounding affinity and the formulas surrounding them is actually much harder. So, once again, we have a formula, And the scheduler may assign a port P to a node N if and only if node affinity, and port anti-affinity hold true. So the node affinity holds true if and only if there is at least one node selector term in the port spec affinity, node affinity, so that the node selector matches the node. Same with the port affinity holds true if and only if all port affinity terms in the port spec affinity, port affinity, match the node. And last, for the port anti-affinity holds true if no port affinity term in the port spec affinity port anti-affinity matches the node. You see the repeating pattern. As soon as a node passes this filter, it may be considered for scheduling. If it does not pass this filter, it's taken out of the list of candidates. So the filter functions select nodes, right? And then the rating functions assign a score for the node. So very similar to the filter function, the rating function applies individual ratings to ports and nodes, right? Sums up this rating, and then for the set of nodes, takes the highest rated ones. So, rating functions. Anybody want to see more formulas? Anybody want to see more graphs? Anything like that? All right, enough graphs, enough math. For more details, please do visit our blog post. We will release a blog post after the KubeCon that talks about the scheduler and will include the nitty-gritty details. But for now, we can do a simple case study, right? So, we have a cluster. And on this cluster, we have nodes with the GPU and nodes without GPU. I'm pretty sure half of you are already sick of this example, but we're going to stick with it. So, and we have a set of ports that do not require the GPU, and we have a set of ports that require the GPU. Now, what is our objective here? Well, we want that every port that does not require a GPU is bound to a node without a GPU. And similarly, every port that requires a GPU shall be bound to a node with a GPU. Okay. Now, as you can see, right now, all ports are eligible to be scheduled on any node in the cluster. So the first thing we're going to do is we add a taint. As soon as we add the taint to the nodes without the nodes with the GPU, none of these ports is eligible to run on any of the GPU nodes and is only eligible to run on the nodes without the GPUs since they do not have any toleration specified yet. Now this is the first trip up. As soon as you add a toleration to the ports that requires GPU, you are not done. The ports that require GPU may be scheduled on the nodes with the GPU, but nothing in the formula, if we remember the formula, tells the scheduler that they have to be scheduled on the nodes with the GPU. You need a different method, basically a different filter for that. So the second thing you do is you label these nodes in preparation for node affinity. Again, this didn't change any of the possible assignments just yet. You have to add affinity to the ports that require GPU. So as soon as you actually do add this affinity, we reached our mission statement, right? The ports that do not require GPU are only eligible to be ever scheduled on nodes without the GPU. And ports that require the GPU are only eligible to be scheduled on the nodes with GPU. Right now, we did not venture into the rating functions. So for example, we did not venture into preferred affinity and preferred anti-affinity. If you want to say something like spread my workload of GPU ports evenly and not just on one machine, you need to venture more into the topic of rating functions, and in that case, port affinity and port anti-affinity. All right, that actually concludes our presentation. If there are any questions, any feedback, more than happy to answer, if I so can.
Maybe you can talk about a little bit more about the ranking functions.
Okay, I actually do not have the ranking functions included in the presentation, and let me try to basically paint a picture without a slide. So for the ranking functions, a common example, where a common user-facing example is port affinity and port anti-affinity. So you can require, right, that a pod does not run on the same node with another pod, right? You can require that, and that is a filter function. So if the node is already inhabited with a pod, right, the scheduler will not take this node into account. However, when you use the preferred qualifier, it has the quality of a rating function. So if the scheduler finds a node that is uninhabited by the port in question, right, it will automatically rank the node higher. And you also have the possibility to add a custom weight to that. However, if the node is pre-populated with a pod in question, right, the node will be ranked lower. However, it will not stop the scheduler from not scheduling it on this node if it doesn't find any other node that actually ranks higher. But I'm sorry, I do not have a formula handy on this one.
For your example, what is the reason that you need to use both taint and affinity? Wouldn't affinity alone is enough?
So I am actually not 100% sure if you can express each and every scenario that you can express with taints and tolerations, also with port affinity and anti-affinity. Not 100% sure if this is a complete subset. However, in this case, you actually can. In this case, I could add labels to these pods, I'm sorry, to these nodes, right? And add labels to these nodes, and then specify a pod affinity for both of the sets of the nodes. So you do have this possibility. There are some reasons when you do not want to do that. One, for example, in this case would be you would actually have to label each and every node, right? And you would have to label each and every pod, right? And that means you have to alter the pod template of any deployment you have, any replica set you have, any cron job you have, any job you have, right? And yes, you could actually come to the same result, right? I'm not sure if this is the case in all cases and under all circumstances, but in this case, you could come to the same result. But it gets unwieldy very quickly. So by expressing it this way, you are actually only touching the nodes and the pods, right, that require GPU, and everything else that doesn't require GPU does not need your attention.
There's a step in there where you have to, and the scheduler is not doing hardware discovery, right? I mean, something has to go through and do the discovery to denote whether it has a GPU or not. It's not built into the scheduler.
Yes, this is absolutely true. So from the point of view of the scheduler, right, GPU means nothing to it. So the taint is an opaque value, right? But this taint matches that toleration, and in that case, in the label there would probably be a mention of GPU, right? But for the scheduler, you are right. For the scheduler, this means absolutely nothing. So this is entirely in your domain and in your responsibility. Yes.
Are there default out-of-the-box ratings
such as just to try to go to nodes that have, say, the most available resources?
Yes. This is actually a tricky question. So number one, I believe yes. Number two, I am not entirely sure which one there are. And most importantly, I am not entirely sure about the rating behavior. What part of the rating behavior is actually part of the contract that the scheduler gives you, right? Or what part is actually basically inside the scheduler and may change without notice from release to release. I have not uncovered that yet. But I do believe, yes, the scheduler does have a tendency to spread out. If this is part of like the contracted behavior, I'm not entirely sure. More digging necessary.
How does the priority, come across, these two filter and ratings, aspect?
So I'm not entirely sure if I understand your question, but I'll try. So the first line of this specification, right, eliminates any node that is not qualified to handle this pod. So this variable now points to a set of pods where the scheduler already determined these pods are qualified to run the node. Now, in the second, the scheduler loops over the individual nodes and establishes the ranking, right, for the node and the pod, and then will select a node from the set of nodes that scored the highest. And if I'm not entirely mistaken, the contracted behavior is if you have a set of nodes with the same ranking, like for example 4 or 5 nodes with the same ranking, the contracted behavior is that it is randomly chosen. I do not think you can place any further constraints on that than saying that it is randomly chosen. Mm-hmm.
So let's say there are two workloads pretty much matching the same set of nodes, but one pod has a higher priority than the other one. Oh. So then how does the...
So when we come to priorities, we actually also venture in a topic that we did not include in this presentation, and that is the scheduler actually has the chance of preempting pods, right? Sometimes there is somewhat of a confusion. I'm not entirely sure I cleared that all up. But there is some kind of confusion between eviction and preemption, right? So eviction is defined as the termination of the pod by the kubelet. It would do so under pressure. Take all of this with a grain of salt. It would do so under pressure of resources. Then the kubelet will terminate. The kubelet will terminate the pod ahead of its time, right? However, also the scheduler does have a chance of preemption. So if a pod has a higher priority, but it cannot be scheduled, the scheduler will examine the workload across the cluster, will find may find pods with a lower priority. And if the scheduler determines that if it terminates these pods, that then the pod with the higher priority can actually be scheduled, it will preempt the pod. Now, preemption in this case, I believe, means that the scheduler sets the deletion timestamp of the pod. It is not going to delete the pod, it is not going to delete the binding, but I believe it sets a deletion timestamp of the pod. which will then give the kubelet a chance to gracefully terminate the pod. Then the resources become available for the scheduler.
How do pod disruption budgets kind of fit into this?
Any other questions, comments?
So pod disruption budget, Kubernetes Scheduler take account pod disruption budget in preemption. But this is not guaranteed, just for your information.
Anyone else? No?
Now, if you don't mind me asking you a question, what do you think about this style of modeling, this style of communicating about Kubernetes and about its individual components, or functionality? If you have any thoughts, if you have any feedback on this style of modeling, I am super happy to hear it. Doesn't have to be now. We're gonna stick around for a few minutes. So if you wanna come around back, that would be cool. Thank you very much. Oh yes, of course.
Yeah, related to that, so currently the documentation is a bunch of descriptions, right? And you kind of have to read it all and kind of piece it together yourself. So the idea is to have a much more rigorous way to describe the behavior. And so this is why we're using this modeling approach, which will include these formulas as well as diagrams. So please, give us some feedback if this is a much better approach in terms of explaining how things work. Thank you.
I was just going to say I would have probably read that more easily if it was written in Go.
Yeah, fair enough. It is, if you're curious, it is a formal specification language that is called Pascal, that translates to TLA plus. That is a language designed by Leslie Lampert. And it's a formal specification language, and it does come with a model checker, so you can actually check if your statements and invariants hold. But yes, you gotta kind of get used to it.
So I'm curious about what kind of checking will you do in this formulation?
So when it comes to that, it is part of what is called invariant-based design, right? So you have an invariant about the state and the state transitions in your mind when you design an algorithm, and then you specify the algorithm, and you check if your invariants actually hold true. So for this one, I had previously I had an invariant that said, if I start with a set of pods from the very beginning, if I start with a set of pods, after the Kubernetes scheduler reaches a steady state, that is, there is nothing else to do, if there is a set of nodes that can host the pods, right, eventually every pod will be assigned to a node. I am not entirely sure if the way I modeled Kubernetes scheduler is incorrect, or if this is actually part of the Kubernetes scheduler, but this is not a guarantee the Kubernetes scheduler gives you. The model checker showed clearly that it can run into situations, right, that even so, with a holistic view of the system, every pod would fit on a node. It can run into situations where it basically starves itself because it made a few bad decisions in the beginning. And it was clear after that that I had to relax the invariance, right? Because I am fairly certain that this is how Kubernetes works, but I need to have it peer reviewed. But I had to relax this invariant and saw Kubernetes does not give me any guarantee. It only gives me a guarantee that it will make an optimal decision each step, but not an optimal decision from a holistic point of view. And you can actually find that with model checking.
Also, part of our process is a mix of interviewing engineers to like ask them the behavior in certain corner cases so we can tell, and then also what's the other thing? Yeah, so we can validate the model, and then what's the other thing we do for the process?
Interviews.
Yeah.
Dig through the source code.
Oh, right. Yeah, right. So look at the source code, because that's the only way you can check what the behavior is. But but the problem with that is just that it's implementation and maybe may or may not be perfect. So that's why we have to check with the engineers.
Yeah, so correct. So overall, no question about it. These processes are or these activities are asynchronous, right? So you would either have to put a review process, like you just mentioned, into place, or this is also the reason why I usually like strongly emphasize what is part of the contract, right? Because as soon as it's part of the contract, I'm gonna include it in the model and I'm gonna include it in the invariance. If it's not part of the contract, I will formulate it so that the model checker can actually choose randomly. Like for example, when I said the highest ranking pod, it will choose randomly. Of course, there is no random in Kubernetes. At least I didn't find one. I think it always takes the first one in the list or something like that. But for the sense of the model, this is now random, right? So as long as the contracts stay in place, the model adheres to it. And if the contract changes, you have to change the model. Yes. If you are actually interested in this detail, I give a little bit of detail and through. There is something that is called model refinements. So you model behavior on a very, very high level, right? And then step by step add refinements, and also prove that the individual step on a lower level is actually a behavior that is allowed on a higher level. So the higher level is the most abstract one, right? Where you could go so far and just say the invariant a pod shall find a node, right? And you go further and further down and add more information. In that case also, the higher your abstraction is, the more its longevity, right? The further you go down and come closer and closer to the implementation, then it is really tied to the life cycle of this component. Yes, please. I'm coming.
So I, for one, have found your presentation very helpful, so thank you. And I think it should be extended to other components too. You know, for example, like the kube proxy or like the kubelet. But I think I totally agree with the gentleman that keeping these in sync and making sure that the formulas they're put in the documentation do not mislead potential like engineers who are trying to understand and figure out why things don't work the way they think they should is going to be key. And also it might require buy-ins from like the community to put effort into keeping them in sync.
Anyone else?
Current schedule architecture scheduled pod one by one, right? So, but in other scenario like big data or machine learning, it's better to schedule all the pods in a group. So, what's your recommendation for this use case? I'm not sure if the next scheduler version will cover those use case, or it's better to extend the scheduler by ourselves.
I am actually, unfortunately, not qualified to speak to that. So I strictly limit myself to modeling how the scheduler works right now. there's a very interesting detail to your question that maybe I don't want to like kill everybody's time that we can talk about after this presentation. Yeah, so take this with a grain of salt. Overall, I'm not the one like qualified to speak to the architectural direction that Kubernetes is going to take.
Last chance, maybe? No? Okay. Thank you very much.